This is the video for accelerated geometry on lesson 16-3, which is the natural base, which is E. Key vocabulary in this section will be natural logarithm and the natural logarithmic function. The essential question is how to use the natural base to solve problems. To begin with, let's look at the natural exponential function, which is just f of x equals e to the x. This e is what we call our natural base. On our graphing calculators, you will notice that the e to the x is in blue above ln. So if you are ever typing in your calculator e to some number or e to the x, you're going to have to hit the second and then hit ln. Okay, so the graph of f of x equals e to the x looks like this. Exponential functions with e as the base have the same properties as functions that we have studied. The graph of f of x equals e to the x is just like any of the other exponential functions, such as f of x equals 3 to the x. The domain is going to be all our numbers. You're not restricted on which x values. You can plug in anything on this side. You can plug in anything over here. So the x values are not restricted. And then the range is y is greater than 0. It does not cross the x-axis right here. It gets really close to it, but it never crosses it. First set of examples, all I want to do is see if we can use our calculator to evaluate e to the x. So for this first one, I want to know what f of 2 is. So we're going to type in our calculator e to the second. And you should get roughly 7.39. So again, to get to your e to the x, you're going to hit second ln, which will bring up e, and then it has a little arrow. And then we want to the second, so you're going to type in 2. For the second one, we want to raise it to the 1/2. So we're going to have f of 1/2 equals e to the 1/2. And on this one, you should get 1.65. Last one, we have f of -1 equals e to the -1, and we should get about 0.37. Continuous compounding formula is A equals P, capital P, e to the RT. Okay, so our capital A stands for our final amount. Capital B stands for our principal, which is what you start with. Your R is your interest rate. Please make sure that you always convert the percentages to a decimal. And T is time in years. So our first example using this says an investment of 1,000 earns an annual interest rate of 7.6%. So first thing I notice, an investment of 1,000, this tells me this is what I'm starting with, so this is my P. Annual interest rate, this is my R, but remember that the R has to be as a decimal, so I'm going to move this 2 places to the left, so it's really 0.076. If the interest is compounded continuously for 8 years, so 8 years tells me that T is 8. Find the final amount. So my equation would be that A equals P e to the RT. So A equals 1,000 times E to the R, which is 0.076, T, which is 8. So we can type that in our calculator just like this. Now I caution you to make sure that when you're doing your exponent here, some of you may want to go ahead and say that 0.076 times 8 and get that answer. of 0.608 and then type in your calculator 1000 e to the 0.608 so that you don't accidentally mess up your exponent here. But others that are really good with your calculators, you can type it in just like you see it. So this is going to give you 1000 times e to that decimal, and your answer should be, we're talking about money, so we're going to go to 2 decimal places, $1,836.75. Let's try another one. We have $2,000 is invested at an annual interest rate of 9%. If the interest is compounded continuously for 12 years, find the final amount. So again, we have A equals PE to the RT, which you're here say PERT. So we see that P is 2,000, R is 9%, but as a decimal, that's 0.09, and RT is 12. So A equals 2,000 times E to the 0.09 times 12. And when we type this in our calculator, we should get 5,889.36. Next, we have what we just talked about, the natural exponential function. Now we're going to talk about the natural logarithmic function. So a logarithm with a base of e is what we call the natural logarithm, and it is abbreviated as ln rather than the log of e. So we won't ever see it written as log base e. You will always see it written as ln. Natural logarithms have the same properties as the log base 10 and logarithms with other bases. The natural logarithmic function f of x equals the ln of x is the inverse of the natural exponential function. So what you might want to write is y equals the log base e of x. We're always going to write it as y equals the ln of x. Okay, so also y equals e of x, or sorry, e to the x, and y equals the ln of x are inverses of one another. So in blue here, we have that same graph that we talked about before, where the domain was all real numbers and the range was y was greater than 0. Well, now in red, we have the graph of the ln of x, and if you notice, in the xy, on the x coordinate here, or the x-axis here, the x's do not go to the negative side. We cannot go below 0 here. So now the domain is x is greater than 0, but our y values are all real numbers. So it's kind of like the domain and the range switched, and it is a reflection across the line y equals x right here. So let's practice using our calculator to evaluate the natural log. So f of 2 would equal ln of 2. So now we don't have to hit the second button. You can just hit the ln button. And when you do that in your calculator, you should get about 0.693. If we find out f of 1/2, then we're going to have the natural log of 1/2. And in our calculator, we should get about negative 0.693. And x equals -1. If you try and do this one in your calculator, you're going to get an error message. Why? Because the function f of x equals the ln of x has a domain of x greater than 0, and -1 is not greater than 0, so therefore you cannot plug in -1. Okay, let's simplify some of these expressions. We have the ln of e raised to the 0.15t. Okay, so really, we know that the ln of e is the same thing as the log base e, because that's what the ln is of e. And so this goes back to our properties of logarithms that says that if you have something with the base here and the base here are the same thing, then that's just going to equal 0.15t. Over here, we have the property that since it's being multiplied in front of that log, we can move it as the exponent. So this is really e to the ln of x plus 1 to the third. So again, there's an imaginary e here. And we have that rule that stated that b to the log base b of x was just equal to x. So now since this base and this base are the same, then that's just going to equal x plus 1 to the third. Again, there's an on number 11 here, the natural log of e to the 2x. There's an imaginary e here, so we can say that that's just 2x. And there's imaginary e here, or this is the log base e of e to the x. So that's really just x, which is 2x plus x is just going to equal 3x. The natural logarithm can be used to solve for an unknown exponent in the continuously compounded formula. So if you remember that formula, it's a equals p e to the rt. So for example, it says, how long does it take for an investment to double at an annual interest rate of 8.1 compounded continuously? So how long does it take tells me that we're solving for t. 8.5 as a decimal would be 0.085. And double means that I want my end result to be twice the amount of what I started with. So if I start with some, like say 1, then I want the final to be 2, because 1 times 2 is 2. So if I set that up, we really have 2 equals. You can put the imaginary 1 here if you wanted to, but it's not going to change our answer. E to the 0.085t. If you notice, it's in exponential form and we're solving for an exponent. So the only other option that we have is to change this to a log form. Well, since we're dealing with the e, we're not going to have the log, you're going to have the natural log. And as long as what I do to one side, I do to the other, I'm not going to change anything. So I can take the natural log of the left and take the natural log of the right. I'm going to come over here now. So that tells me that the natural log of 2 equals, remember this is really log base e of e, so then that tells me that that's just equal to 0.085t. And now I can solve for t by dividing both sides by 0.085. So the natural log of 2 divided by 0.085 is my answer to t. So when I do that, I get 8.15 is my t. So the answer says, how long does it take? We're always going to take this and round up. So my final answer here would be 9 years. Let's try another one. It says, how long does it take for an investment to triple? So I know the time is what I'm solving for. For an investment to triple, it tells me that my final amount has to be 3 times the amount that I start with. So I'm going to start with 1, and 1 times 3 is 3. And my interest rate of 7.2% would become 0.072. So I have 3 equals 1, E 0.072 t. If I divide by 1, it's not going to change anything. So really that's just that. Again, it's an exponential form and I can't go any further, so I'm going to go to the log form. So I'm going to take the natural log, since I'm dealing with E, of both sides. So now I have the natural log of 3 equals 0.072 t. Opposite of multiplication is division. So I'm going to type in my calculator the natural log of 3, divide that by 0.072, and we should get 15.26 equals t. I'm going to round that up, so my final answer is going to be 16 years.